Hello everyone, and welcome back. Last time we were looking at conservation of momentum and the rocket equation, how momentum was conserved when a rocket threw out some of its material as burned up exhaust. What we're going to do now is start taking a look at a different kind of motion, which brings us to section number 9, rotation. What we're going to do is we're going to take a look at what happens when objects rotate or spin around, something like this wheel. That is going to give us some very different kinds of motions, with some different properties that will have some very, very interesting aspects. Before we look at an object, a solid object rotating, let's look at a point object that's actually moving around in a circle, what we will call uniform circular motion. Let me give you an example and explain why we call this uniform circular motion. So let's imagine we've got this little mass. I've got a mass here on the end of a string, and let's imagine that this thing is spinning around. So it's going around like this. Okay? It's going around in a circle. We notice it's going in a circle, assuming I can keep my hand completely stationary. It's moving around in a circle. Can you see it? And let's assume that it's moving around at a constant speed. So we've got an object moving around in a circle, and we'll assume it's moving at a constant speed. That is the uniform part of the circular motion. So we've got circular motion, the object is moving in a circle, and the uniform part is assuming it's at a constant speed. How can we describe this motion? What kind of aspects can we use to describe this? Well, first of all, what's the size of the circle? We will define this with a center, so let's assume this is the center. The distance from the center to the object, assuming it's a point-like object with not a large extent, to the center of the object, that is the radius. So r is the radius of the motion. Then how much time does it take for one complete circle? So imagine it's going around. To make one complete circle, the time that takes we'll call the period. So the period is the amount of time that the object takes to make one complete circle and come back to where it starts. And the symbol that we'll use for that is a capital letter T. We've got to be a little bit careful to make sure we keep in mind, are we talking about T, capital T for the period? Like you can imagine it comes from time. We don't call it with a capital P because we've already used that for momentum. But make sure you don't confuse that with the capital T for tension, because there's also going to be a tension in this problem. So we've got a tension acting on it. Now let's think about this. How are these related? The radius, the tension, and the speed. Well, if we think of the speed, which is v, as the distance per time, how far does it travel in a certain amount of time? Well, for one circle, what's the distance traveled? It'll be the circumference of the circle, so that would be 2 pi r. And how much time does it take to make that one circle? The period t. So we've got a relationship between the speed, the radius, and the period. V equals 2 pi r over t, or you can move these around and you'll have t equals 2 pi r over v, whatever you want. But we've got this very simple relationship between those three quantities. Now what I'd like to do is think about this motion, and I want to ask you a question. I want you to think about this for a second. Assuming that we have uniform circular motion, is this object accelerating? Is it undergoing an acceleration? Well, you might think, well, no, it's got a uniform speed. It's not accelerating. It's not speeding up, not slowing down. So no, it's not accelerating. But the acceleration is not the rate of change of speed. We defined our acceleration as the rate of change of velocity. Is the velocity changing? The speed is just the magnitude of the velocity. Is the velocity changing? Well, the velocity has two properties. It's got magnitude and direction. It's a vector, it's got direction. Is the direction of the velocity changing? In that case, yes, it is. If we think about this motion again, And I'll try and do this a little bit slowly, and we'll see if we can see what's going on. So as this goes around, when it passes this point, how is it moving? Well, you might notice that it seems to be going up, straight up. At the top up here, I hope I don't hit myself. At the top, what's it doing up here? Well, you might notice that it's going this way. Hopefully you can see it. Hopefully it's not going too fast for you to see it. It's going to your left. Down here at the bottom of the motion, what's it doing? Well, it seems to be going this way, to your right. And over here, it's going down. So the direction is definitely changing. The direction is not constant. Well, if the acceleration is the rate of change of the velocity, and the velocity is a vector with magnitude and direction, if the direction of the velocity is changing, we must have an acceleration. So how can we determine what this acceleration is? Let me just write this. Let's say I'll write it over here. So we defined the acceleration vector as the rate of change of the velocity over time over a very, very small time interval, the limit as delta t goes to 0. So what does this mean? We need to look at the change in the velocity. So we'll pick an initial and a final time. We'll look at how the velocity changes. We divide that by delta t, and the limit, as we look at a smaller and smaller time interval, that should give us the acceleration. Well, we're going to do this in two parts to try and figure out what this acceleration is. We're going to figure out what's the direction of the acceleration, and then what's the magnitude of the acceleration. But let's keep in mind how we're going to do that. We have to find a change in the velocity, and then the direction of that change in the velocity, that direction will be the direction of the acceleration. The t doesn't change the direction of the vector delta v. So we'll look at what's the direction of delta v as the time interval goes to 0. So what does that look like? Well, let's imagine that we'll start with our initial point right here. And let's assume that it's going this way, like I was spinning the weight. So here, what's it doing? Well, hopefully you'll remember over here, it was moving straight up. So that's our initial velocity vector. Now let's look at it slightly later, over here at this point. What's it doing here? Well, it's going to be moving in this direction, like that. So that's our final velocity. So v initial, v final. Now what do we want? We want delta v. Delta v, which is v final minus v initial. So we have to subtract the initial vector from the final vector. Okay, so here's our initial vector, here's our final vector. I'm going to get rid of some of this and redraw this to make it a little bit easier to see, so I'll be right back. So I've redrawn our same diagram again over here. So here's our object going around in a circle. At some point here, it's got a velocity that looks like this, say straight up. There's our initial velocity. At some time later, we've got a final velocity over here, which is going to be going over that way. So here's v initial, here's v final. Now, what do we want? We want the change in the velocity, delta v, which is v final minus v initial. Let's remember, how do we subtract vectors? Let's imagine we have two random vectors, say a, some vector a, and some vector b. So a and b. And let's imagine that what we want is we want to find what is b, b minus a. What is b minus a? Let's call that just some vector c. The first thing we need to do is put them tail to tail. So let's put the two vectors a and b tail to tail. So we've got a, looks like this, b then looks like that, there's b. Now c is b minus a. Let's bring a over to the other side. What do we have? b equals a plus c. So what is c? C is the vector that we would have to add to a in order to get b. How do we add a vector? How do we add vectors? We put them head to tail. So we'll take the tail of c, put it on the tip of a. So we'll take the tail of c, put it on the tip of a, And then to get b, it has to come over here to the tip of b. So that's the vector c. So we notice, yes, a plus c equals b. Great. So what does that tell us about the difference? C, b minus a is a vector that points from the tip of the second vector to the tip of the first vector. So let's remember, when we subtract two vectors, say b minus a, we end up with a vector that goes from, first we put the vectors tail to tail, and the difference then is a vector that goes from the tip of the second vector to the tip of the first vector. Okay, great. What are we doing? We are taking v final minus v initial. So what is that going to be? It's going to be a vector that goes from the tip of v initial to the tip of v final if we put them tail to tail. So the first thing we have to do is take v initial and v final and put them tail to tail. Now I've enlarged our diagram here so that these vectors will match the length of some arrows I have. So we're going to take v initial here, and then v final, which is up here, but I'm going to bring it down and put it tail to tail with v initial. There we go. So what is v final minus v initial? It is a vector that goes from the tip of the second to the tip of the first. So it is going to be a vector that looks like this. There. And that is the vector delta v. It goes from the tip of v initial to the tip of v final. Great. That's the direction of delta v. But remember, for the definition of the acceleration, we need to look over an infinitesimal time interval. In other words, we need the time difference between the initial and final points to get smaller and smaller. So what does that mean? Well, here's our initial point. Here's our final point. If we let the time difference go to 0, that means this point is going to get closer and closer to this one over here, which means the direction of v final is going to do what? Well, as we move over here, the direction of v final is going to rotate over toward v initial, always keeping tangent to the circle. That's what these vectors look like. They look like they're tangents to the circle. So as delta t goes to 0, v final is going to rotate over this way closer to v initial, which means in this diagram, what's going to happen, v final is going to rotate over this way, closer and closer and closer to v initial. Well, what happens to the direction of delta v? Notice that when v final is over here, delta v looks like that. But as v final comes over here, delta v seems to get more and more horizontal. So that when the time interval is very, very small, these two tips seem to be right at a horizontal difference between them, like this. So what we notice is that as delta t goes to 0, delta v becomes the direction, we're just thinking about the direction of delta v becomes horizontal. Horizontal. So what does that mean? At this point, as delta t goes to 0, the direction of the acceleration, because remember, the direction of the acceleration was same as the direction of delta v, is horizontal, which means where is it pointing? It's pointing toward the center. The acceleration is a vector that points toward the center of the circle. We call that a centripetal acceleration. Centripetal means pointing toward the center. Centripetal, pointing toward the center, acceleration. It's an acceleration that points toward the center of the motion. Actually, that makes a lot of sense. If we go back to our mass on the string, what force is acting on the mass to keep it going around in a circle? It's the string. It's the tension in the string. The only thing, assuming we can ignore gravity. Just imagine it's going around in a circle without the effect of gravity. What's making it go around in a circle? It's the string. If I were to let go of the string, the mass would go flying off to the side, like this. Okay, I let it go a little bit too early so that it went up that way. But if we could actually let it release it, we'll try it again and see if I can release it right at the top of the motion, and let's see what happens. So if I could release it right up here, see if I could do that, it shoots off that way, the direction of the velocity. Okay, but what's the direction of the force? Let me grab the string. What's the direction of the force that the string is exerting on the mass? Well, it's a tension, and we know tensions are always in the direction of the string. I can't pull on something sideways with the string unless I put the string up this way and pull on it like that. So, as the mass is going around in the circle, what direction is the tension? Well, the string always points towards the center of the circle. So the force that the string is exerting on the mass is always toward the center of the circle. If the force is toward the center, F equals ma, the acceleration must be toward the center. So it makes sense that we end up with a centripetal acceleration because it seems like we have a centripetal force that's acting on it. Okay, well, great. So we're halfway done. We've got the direction of the acceleration. Let's remember, what are we trying to do? We've got an object going around uniform circular motion. What we have found is that the direction of the acceleration at any point in the circle, we could generalize this. When it's here, the force is that way, or the acceleration is that way. When it's up here, the acceleration would be that way. When it's over here, the acceleration would be that way. Okay, so the acceleration is always pointing toward the center of the circle. It's a centripetal acceleration. That's the direction. What's the magnitude? Let's see if we can figure out what the magnitude of the acceleration is next. Okay, I need to redraw some diagrams, so I'll be right back.